So I was saying thank you for inviting me and the opportunity to present my research. My name is Welbanks. I'm a PhD student at the Institute of Astronomy. I am on my last year of my degree. And I am being supervised by Dr. Nico Madhusudan, and this research has been possible thanks to support of the Gates Cambridge Trust, who helps financing my PhD studies. And today, I am very happy to talk to you about an aspect of the research that I've been doing, which is looking into possible mass-metallicity trends in transiting exoplanets. And this work has been done in collaboration with other researchers whose names are in the screen. And again, I'm very excited, and I thank you for the opportunity. I hope in the future, when things are better and we're not in the middle of a pandemic, I get to see beautiful Canarias. I want to talk to you today about transmission spectroscopy of exoplanets particularly, and how as a field, we have been able to go from studies of individual planets where we are looking at the composition of their atmospheres to, thanks to the increasing number of observations, compile planets and look at them as an ensemble and study them as a population. And from different ensemble studies, there have been lessons learned and insights into some of the challenges that come when trying to interpret transmission spectra. And this will lead to our latest work on an extensive chemical survey of the compositions of these exoplanets. So first things first, you may have seen a diagram similar to this. This shows the geometry with which we can make observations of transiting exoplanets. There is a star that is not our sun, and this star is host to a system of planets. In this case, there's one planet that is going around its host star. And as it goes around the host star, it has eclipses. When this planet goes behind of its star, we get what we call a secondary eclipse. And in this type of configuration, we see the thermal emission of the planet. And when the planet goes in front of the star, the planet blocks a little bit of light from the star, and the light is going through this blue annulus here, that is the atmosphere of the planet. And this is a primary eclipse. And these type of observations, the primary transit, is the ones that I am going to focus on today. There is this animation that I really like by Goddard Media Studios that shows this a little bit more. There are light rays coming from the star towards the observer, but as they get to the observer, they reach the atmosphere of the exoplanet. And some of the light rays get absorbed by the atmosphere of the planet. In this case, it's shown by the blue light rays in this animation, and some of them get transmitted, and they go through the planet atmosphere, and they reach the observer. Now, the impact of having this configuration is that the size of the planet changes depending on the wavelength that we're looking at it. And as a result, the amount of light that the planet is blocking from the host star changes. That is what this second animation is showing. In here, the apparent size of the planet is a function of the wavelength, and at some wavelengths, the planet looks smaller or larger. In this particular case, the green wavelength, 2.1 microns, the planet is the smallest, and as a result, it blocks the least amount of light, whereas in the yellow, the planet looks the largest, and it blocks the most light. And it is this apparent change in size that we're interested in looking into. Something that really drove the point home for me was seeing this picture of Earth with the moon on the background. And here you can see this beautiful blue halo that is Earth's atmosphere. And just like if we were doing an eye exam, I'm going to go back and forth between the different slides. So I'm going to show you what happens when you look at this picture in 8.6 microns. And you see that the atmosphere seems to have changed relative to the previous picture, and at 9.6 microns. So I'm going to go back and forth. And here you see that between the three pictures, the atmosphere of Earth seems to change in size. Earth is experiencing an apparent change in size, and this is because At 9.6 microns, ozone absorbs light, and we are observing the ozone layer on Earth. So this is really cool. Something that we use for exoplanets can be tested here on Earth, and this is what we're looking at. And this is a cartoon of what I'm trying to say. We have the host star, the light rays are going through a planet atmosphere, and it is the chemical composition of that atmosphere, the molecules and atoms in that atmosphere that are absorbing light. And the residue is what we get here in our telescopes. And in understanding that residue, we get the fingerprint of the composition of this exoplanet atmosphere. Reality may be a little bit less romantic, although I'm showing observations that are a little bit older. These are observations from 2013. I have adapted them to bring home the point that we are observing an apparent change in size. On the x-axis, I'm showing here the color or wavelength. On the y-axis, the size of the planet. And we see that at some wavelengths, the planet seems smaller, and as a result, blocks less light. And on some wavelengths, it is larger, and it is blocking more light. So it is this pattern of increasing and decreasing planet size that we're trying to understand. And to explain these observations, we can ask three questions. First, what is the chemical species present in the atmosphere of this exoplanet that is responsible for that fingerprint? Second, once that we know that a species is there, how abundant is such species in the atmosphere of the exoplanet? And third, a larger goal is, what does such abundance tell us about the planet's birth and history? In other words, we could try to link the present composition of the planet that we're observing to its history. And that is a frontier of what we can do with this type of observations. So let's look first at what chemical species are present. Here I'm showing a plot from the work of Sid Gandhi and Madhu from 2017, in which they are showing the cross-section of different molecules. That is the size, effectively, of different molecules as a function of wavelength. And we see that different species have very specific fingerprints and distinct patterns that distinguish them from others. For this particular plot, we can look at the purple curve, the purple wiggly line, and that corresponds to water. And water has a distinct feature at 1.4 microns, this bump, and that bump is something that has been used in the field to detect water in many, many exoplanets. And in the last almost 20 years, there have been many planets with many detections of multiple species, going from the first detection of an atmosphere in an exoplanet and the detection of sodium in the hot Jupiter HD 209-458b in 2002, where they show here a difference of the relative flux, and this decrease on the relative flux was assigned to sodium. So the fact that they are seeing a decrease in flux, they said, well, this is a detection of sodium. Something very interesting that I like about reading the abstract of this paper is that they mention how the size of this feature is relatively smaller than models that consider presence of clouds. So the size of the feature that they saw for sodium was smaller than expected. So that indicated to them that something was going on in the atmosphere of this planet that was making the size of this feature smaller. And that has been also seen in many other exoplanets with different species. For example, here, these are observations with the Hubble Space Telescope of the same hot Jupiter, HD 209-458b, where you see this bump that I was trying to mention in the previous slide at 1.4 microns, something similar for the hot Jupiter WASP 43, a bump at 1.4 microns, WASP 12. So it is really, really great that the current state of the field gives you exquisite observations where almost by eye, you can pick up the features of these molecules and fit them with pattern recognition with your brain and say, well, yeah, I see a bump here at 1.4 microns, and I know that water absorbs there, so this is a water feature. And similar things can be done with ground observatories. For example, this is a feature of sodium, a little bit short of 0.6 microns, observed in WASP 96. This is work done by researchers at IAC at Canarias, led by Guo Chen and Enrique Payet, that we were lucky to be part of, where there are indications of sodium, with this feature a little bit short of 600 nanometers, of potassium, with this feature a little bit short of 800 nanometers, and the first indication of the possibility of lithium in the same planet with this middle feature. Taken with observations at the Gran Telescopio Canarias. And that combination of observations from ground-based facilities and space facilities has also led to studies like the study of Wickford in 2018, where they combine observations from space observatories, HST, and ground-based facilities to provide a full covered spectrum from the optical wavelengths to the infrared, and also includes observations of Spitzer. So we're getting exquisite observations with wavelength cover that is extended, that gives us information about the possibility of water, of sodium, of potassium, clouds, and hazes. And that is something that we want to learn more about. We want to know what these detections tell us. And from these detections, as I've kind of implied, you can learn something about the atmospheric composition of these exoplanets, the pressure temperature profile of these exoplanets, and the presence of clouds and hazes. In order to do so, thankfully, the data is so good that for some features, we can almost fit it by eye, as I was saying earlier. We can do something, for example, forward models that is more precise, where one determines some input parameters about the pressure temperature structure of the atmosphere. One says determines what the composition of the planet may be, and some input parameters like the size of the planet, the size of the star. And with those input parameters, opacity sources are calculated, radiative transfer is solved, and out comes model spectrum. And that model spectrum can be compared to the data. And by some metric, one can choose whether the data is fit by this model and provide an explanation for the observations. In forward models, there are two main ways of proceeding, two main frameworks. One of them are self-consistent models. In self-consistent models, it is assumed that the properties and processes in this exoplanet atmosphere are known a priori. And there are some equilibrium assumptions, like radiative convective equilibrium or chemical equilibrium, that determine what the composition and the reactions in this planet are. And with these controlled conditions, the output of the spectrum follows these expectations. The issue with this is that in solving all these conditions, the computation time may be expensive. Instead, what one can do is follow a parametric model, where the composition and the structure of the pressure temperature profile of the atmosphere is parametrizable. And these parameters allow you to constrain the data, derive the constraints from the data, unlike the self-consistent model where the constraints are imposed on the data. So in other words, by allowing for a parametric model, we can let the data speak for itself and give us the constraints. And because we are not forcing some of these assumptions about equilibrium, the model can be faster to compute. So these are the two main ways in which one can produce a forward model. Now, the issue of using only one forward model is that while a solution may be found, we don't necessarily obtain any information about the statistics of such model parameters and the statistics of the input that we're putting into our models. And we don't know if the solution that we found is the unique solution or a unique solution. So in order to tackle this, one can follow the inverse problem, or what is known in exoplanet literature, retrieval. And in a retrieval, what happens is that the observed spectrum is input into a optimization algorithm. And the optimization algorithm samples a parameter space, gives some input parameters. Those input parameters are used to generate a model. And the parametric model is faster in this particular case. It provides a degraded spectrum, which is then compared to the observations. And in this iterative process, the parameter space is searched, and once the optimization algorithm has converged, the output are the posterior estimates and model evidence for our model in case. So to summarize, a retrieval allows for the exploration of the model parameter space. It provides a fit to the data, but it also creates a posterior probability distribution for all the model parameters. And therefore, we can use this to try to understand what are the constraints the data are providing us. So for a retrieval, we want a reliable data set, good and fast model, and an optimal optimization algorithm, a good optimization algorithm that is robust statistically and provides a good search of the parameter space. And this is what we've used in the work that I'm presenting today. And the particular model that we used is a parametric model. And this model solves line-by-line radiative transfer in a one-dimensional atmosphere. And this one-dimensional atmosphere follows hydrostatic equilibrium. The pressure temperature profile in this atmosphere is parametric, and so are the chemical compositions. So we fit for the abundance of these species. And importantly, we allow for the presence of clouds and hazes in homogeneous cover of the atmosphere of the planet. So that's it. We can detect species, and we can provide some constraints on the models that are in the parameters that are going into our model. And as a result, we can understand what are the abundances that fit our data. But now that we know that, we want to know what do these compositions tell us. And as I mentioned earlier, this atmospheric composition could give us hints into the history of the planet, where it formed, how it formed, has it migrated, what has going on. For example, in the solar system, we know that the gas giants have supersolar enrichments of carbon, sulfur, and nitrogen. This is by measurements done by probes that have been sent to these gas giants. And these observations support the formation of, for example, Jupiter by a model called core accretion. And the core accretion model expects that other species, like, for example, oxygen, will be also supersolar, will exhibit supersolar enrichments. And this is a great point for me to introduce this diagram. So here, I will be referring to this diagram again. On the x-axis, I'm showing the mass of the planets. On the y-axis, I'm showing the metallicity. And this gray line, horizontal gray line, is a solar value. So this is the abundance of a particular element in the sun. In this case, the star that the planet is going around, because these are solar system planets, our star. And these are the abundances of the gas giants based on CH4 measurements, and these are carbon abundances. So we use the CH4 that is measured in these gas giants, and we relate them to the carbon abundance. And these are the error bars of the measurements. And the point here is that these error bars lie above the solar line. So that's what I mean when we say that we have a supersolar enrichment. The abundance of carbon in these planets is higher relative to the expectation of the sun. And it is common to fit a line to these observations to see if there's a trend. So if planets form by core accretion, we would expect that they would match this behavior. And that is what we are interested in looking. We're interested in comparing multiple planets that are outside of our solar system to what we know about our solar system, and perhaps understand more about possible formation mechanisms for planets. Now, one-to-one comparison is difficult between the solar system gas giants and exoplanets, because while we have measurements of water observations on many exoplanets, we don't have water oxygen measurements for the gas giants in our solar system. And when I started my PhD, I found that it's really amusing, the fact that we know more about some exoplanets than we know about planets in our own solar system. And the reason for that is that the gas giants in our solar system are cooler planets, and as a result, the water has condensed out to deeper parts of the atmosphere, and sending probes is the only way in which we can actually get measurements of the water abundances, but getting so deep in the atmosphere of these gas giants has proven to be very difficult. On the other hand, exoplanets are really hot, the ones that we have been observing, very close to their stars. And as a result, there's water vapor in their atmospheres, and that is what has facilitated the measurements of water. And then, now that we have this idea, we can go into what has been done about trying to understand exoplanets as an ensemble, as a population of itself. So I want to have a little bit of a recap of what has been done. And one of the first studies that looked into analyzing populations of exoplanets is the work of Madhusudan 2014, where constraints of water abundances for 3 hot Jupiters were obtained. These were HD 189.733b, HD 209.458b, and WASP-12. And you can see in these observations that almost by eye, you can pick up the water feature that I was referring to earlier, this bump at 1.4 microns, and that different planets have different sizes of this feature, and the different resolution of the observations also gives you more information, or be able to pick up this feature better or worse. And one thing that was found is that the size of these features were muted. They were slightly smaller than expected. These features were around 2 scale heights, whereas for a fully saturated feature, you would expect 5 to 10 scale heights. So they were smaller. And what they did, Madhusudan 2014, is that they performed a retrieval study, and they derived water constraints for these 3 planets. And here I am showing their posterior probability distribution, where the x-axis shows the volume mixing ratio of water, and this dotted line shows the solar value. So the abundances for all 3 planets lies on the left of the solar value. So to within 1 sigma, these very nicely peaked posterior distributions, constrained posterior distributions, show subsolar water abundances. So the conclusion of their work was that they were finding lower abundances than solar abundance predictions. It was very puzzling. 2 years later, a study by David Singh in 2016, Singh et al., performed a study of 10 hot Jupiters. And now in this case, they had observations for many planets on the near infrared and in the optical, where observations of sodium and potassium are possible, and the presence of clouds and hazes. Now, in their study, they did not use a retrieval. Instead, what they did is forward models, and these forward models were isothermal. And in their synthetic spectra, what they also included the presence of clouds, which was not considered in the work of Madhusudan 2014. And Singh et al. 2016 conclude that this primordial water depletion during formation that was hinted at from the previous study was very unlikely, and that instead, these small features were due to clouds and hazes. And so this was very different to the study of 2014. It's not that there was less water, it was just that clouds were muting our features and we were not able to see them. Later, in 2017, 1 year later, people from the same study led by Barstow in 2017 performed a retrieval this time using optimal estimation. And the results, using a consistent set of models that did include clouds and hazes, found that there was a variety of clouds and hazes, but the majority of the planets were consistent with abundances that were subsolar, 0.01 times solar to solar. So this highlights something very important. An analysis of the same planets using forward models versus retrievals leads to different conclusions, and that is due to using a more robust parameter search with statistical constraints. And it is absolutely the opposite conclusion. In this case, they were finding subsolar water abundances. And their abundances of sodium and potassium were generally inconclusive. And there was another study last year by Arasipin-Haas et al. In 2019, where they looked at the same 10 planets now using a Bayesian retrieval approach. They find again a variety of clouds and hazes, but again, subsolar water abundances. And they show this plot very similar to what I was showing you earlier, where the solar system planets are shown, and here in blue, the results of their retrievals. And you see that the error bars of their abundance estimates are consistent with solar values or subsolar. And the planets with the tightest constraints, with the highest precision, like HD 209, are strongly subsolar. So this highlights that the importance of doing a retrieval study. But this also leaves a question. What is going on? Is it that the metallicity in these planets is overall lower? All the metallicity in these atmospheres is lower, or is oxygen depleted in this atmosphere? For example, is the ratio, the C2O ratio of these planets higher than expected? So this is a degeneracy. We don't know why are we observing these water abundances. And also the fact that some studies included clouds and some others don't, but that drove a difference in the inferred abundances shows that there are some challenges when trying to interpret transmission spectra. Some of these challenges were, as I mentioned, the presence of clouds and hazes and how these may affect the derived abundances, and how observations over a limited wavelength range can affect the derived abundances. So for example, the study of Pinhas et al. Showed that when you only use observations in the near infrared, your posterior distributions, your precisions are around 1.5 decs. Whereas if you include observations in the optical and you are able to constrain the presence of clouds and hazes, your abundance estimates become tighter, more precise, and can be as small as 0.5 decs. So it is important to consider the wavelength range. And that is what motivated us, that motivated me to look into what are the challenges. How is it that limited isobaric, isothermal models can affect the derived abundances? How is it that clouds and hazes can affect your abundances? How is it that data can affect your inferences? And what happens if you consider limited absorbers? For example, what if there's sodium in the spectrum, but you're not considering it? Does that affect the retrieved abundance that you have for another element? And we did that by looking at the prototypical hot Jupiter HD 209-458b. We looked at observations in the near infrared and in the optical. And what I'm trying to show you here is that we looked at a variety of models that were very, very simplified isobaric isothermal case one, all the way to very complex models that have homogeneous clouds and hazes, use all the data, consider presence of sodium, potassium, water, etc. And the point being here that different models provide varying degrees of fit to the data. But more importantly, I want to show how different models can become overconfident in their abundance estimates and can be biased. So for example, here using a simpler model gives you a different result than when you start considering clouds, and how clouds are very important in being robust in your estimates, how including optical data is very important, and including sodium and potassium for those observations that show absorption due to these species is important. But there is a point where your model complexity can keep increasing, but your abundance estimates, your precision doesn't improve. So your model efficiency kind of converges. And it was good to know how much more complex should your models be, and what is the trade-off in the precision that you're getting. So the findings were that in order to obtain precise estimates of the chemical abundances, one must A, use high precision optical and infrared spectra, that one should include variable cloud coverage, include prominent opacity sources, and that when analyzing observations in the optical, it is very important to consider sodium and potassium to provide joint constraints about these abundances and the cloud and haze properties. And if instead one was to use simplified models or simplified assumptions, these can lead to biased results. So now that we had a better idea of how complex should the models be and what is important to put into our models, we decided to go ahead and perform an extensive survey of the atmospheric chemical compositions of exoplanets. And for that, there were two important elements. First, we used the most up-to-date sodium and potassium cross-sections in this case that there are H2 broadened, and so that we have these wings that will give us more information about the observations that we're getting in the optical, and our latest and up-to-date retrieval model that uses an optimization algorithm. In this case, it uses multiness. It performs a proper exploration of the parameter space. We had a complex model that included clouds and hazes, and this all in order to get a good estimate of the posterior probability distributions of the model parameters. Important, as I mentioned, was to get planets that had extensive observations. So here I'm showing you a plot from 2019 from Madhusudan, where there's planet mass and planet radius. These are planets observed, and we looked at, and the colors here are planets that have had spectroscopic observations with HST and with ground. So we looked at the literature and we tried to obtain all the planets to date that had observations both in the optical and the infrared, or in the optical that could give us information about the abundance of sodium and potassium. And the importance of looking at these three species and going beyond water is that if we understand what's going on with sodium, potassium, and water, we could perhaps understand if, and break this degeneracy of understanding whether all the metallicities are lower in these exoplanets, or if it's just that water, oxygen, is depleted. So that is what we had in mind when we were starting this study. And in total, we looked at 19 exoplanets. And the data went from mini-Neptunes like K218b with equilibrium temperatures of roughly 300 Kelvin to hot Jupiters with 2 times the mass of Jupiter and temperatures of 2,700 Kelvin. And in doing our analysis, we were able to confirm 6 planets with strong sodium detections, 6 planets with strong potassium detections, and 14 planets with strong water detections. And I want to show you some of the spectra so that you see how there is a variety of water features in the transmission spectroscopy that we are analyzing. There is this familiar bump, and the exquisite data is allowing us to find it in many, many planets, but the size, the shape of this is changing. And some planets, perhaps it's a little bit harder to identify this bump. And that is why it's important to do a full parameter search with retrievals to look at all the possible scenarios that could explain the data. And we did the same thing with the observations in the optical, and we see observations of the sodium peaks, the potassium peaks. For example, here's again WASP-96, where we see the broadened wings fitting the data that perhaps is indicative of the lack of clouds or clouds not muting these features. Other planets, again, WASP-127, where we see a slope, but still see observations of sodium, potassium, and lithium. And ultimately, there is a variety too in the presence of sodium and potassium in these exoplanet atmospheres. And that is the importance of using ground-based facilities to help us in understanding these exoplanets. So now that we have looked at the data, retrieved the parameters in this data, we can try to put the results in context. And I go back to this plot. Again, I'm showing you here the Mass-Metallicity trend derived from the solar system. And what I'm going to do next is show you the constraints for each species, sodium, potassium, and water. But they are all relative to stellar. So they have been normalized to the metallicity of their host star. Here is first, sodium. So we see that the abundances of sodium are mostly consistent within 1 sigma with the stellar value or higher, and they are roughly consistent with the solar system metallicity trend, aided largely by large error bars. A very similar picture is painted with the potassium abundances. The values are consistent with their stellar values or higher. So there seems to be stellar or superstellar abundances for potassium too. However, when we go to water observations and we try to use it as a proxy for oxygen, we see something very, very different. We see that for the gas giants, the abundances are consistent with stellar or substellar, especially for planets that have the tightest constraints. And for the sub-Saturn, mini-Neptune items, objects, the abundances are stellar or superstellar. With the one exception of this planet here, WASP-39, where the data was not robust enough to help us find a unique solution to the data. Here, our models found two possible solutions that were able to fit the data, so the data was not robust enough to give us a unique solution, and that's why we're plotting these two solutions. So now I'm going to show you all of them together. And a very important point is that for planets that have observations of all three species, water, sodium, and potassium, interestingly enough, the alkalis are always higher than the water observations. Any planet that had water, sodium, and potassium were higher than the water abundance. And we can do something similar to what we do of the solar system, and we can fit a trend to what we see in the water observations. And here I'm showing you the contours at 1 sigma and 2 sigma. And we see that the trend that comes from the water observations is not consistent with the solar system trend. And statistically speaking, the water trend, cannot explain the solar system observations above 6 sigma. And the same is true. The solar system trend cannot explain all the water observations in exoplanets to above 6 sigma. So this is very interesting. The conclusion then was that water is common. Water seems to be all over the place. There's many planets that exhibit water absorption, yet somehow it seems to be a little bit smaller in lower abundances than expectations. And we see a trend. We see a trend of increasing water abundances with decreasing mass that goes generally from substellar values for the gas giants to stellar to superstellar values for Neptunes and mini-Neptunes. And the water abundances give us a trend that is significantly lower than the mass-metallicity relation that we see for carbon in the solar system gas giants, and similar predictions for exoplanets. Now, interestingly enough, the sodium-potassium abundances for the gas giants, where we can observe them, are stellar or superstellar and generally consistent with each other, meaning that when we see potassium enriched, so is sodium. And because we see that the alkalis are enriched, but there seems to be a water depletion, this is indicating that the low water abundances are likely due to low oxygen abundances relative to other elements instead of overall lower metallicities. This breaks the important degeneracy that we had from previous studies. This seems to indicate that it's not that the total metallicity is lower, but it's just that there seems to be an oxygen depletion. And it's an oxygen depletion relative to other elements. So with that, I want to start summarizing and giving you my conclusions. And when analyzing spectra of transiting exoplanets, it's very important to know which considerations are very relevant to our models and what will give us will help us derive precise abundance estimates. And that is the use of the latest cross sections. That is very, very important. Have robust models and have a broadband transmission spectrum. Our latest work has shown a trend of mass metallicity, and it finds that from mini-Neptunes to hot Jupiters, water abundances are generally consistent with or depleted compared to equilibrium expectations. And it is significantly lower than the solar system trend, solar system metallicity trend. On the other hand, again, the sodium and potassium abundances are consistent with or higher than those of their host stars and generally consistent with the solar system trend. So because we find low water abundances in the hot gas giants while we find high alkali enrichments, it seems to indicate that there are superstellar carbon to oxygen ratios or sodium to oxygen ratios or potassium to oxygen ratios, meaning overall, there seems to be a superstellar or stellar metallicity, but oxygen is depleted relative to other species. And if true, this consistent depletion of water abundances seems to suggest that there are different formation paths for these close-in exoplanets compared to the solar system, meaning that not all exoplanets formed in the same way as the planets in the solar system formed. And lastly, importantly, the differing trends in the abundances that we're seeing, the fact that the alkalis were enriched but water was depleted, argues against models that assume that the metallicity or the C2O ratio are the parameter that it should be fitted, and the chemical equilibrium models could be lacking in finding the subtleties, because we're seeing that different elements can be differently enhanced. And lastly, it is important to keep bringing the number of observations, and the future work will look into expanding this sample with more ground-based facilities, with upcoming space observatories. We will populate more of this diagram. And ultimately, I'm excited about finding outliers to this trend, because it will just show a wider variety in the formation mechanisms of exoplanets. And while my work has been on doing the retrieval analysis and providing these abundance estimates, I look forward for these inferences to be used in informing planetary formation models. There are more details in the paper, which I'm showing here, and I will finalize. I am putting back my conclusions here, and I thank you for listening to me.
Okay, many thanks. Let's have a look at the conclusions for a moment. Yes. Many thanks, Luis, for this very, very well presented talk with a very nice introduction. So we get now to questions. And as the first thing, I will unmute everyone. So if you have something noisy in your background, please mute it again. But I'll unmute now everyone, and then people should ask questions. You may also use, if you go to the participants panel, the raise hand feature, if you find it. That's the next option. And the last option, if you want to ask questions, is you can use the Zoom chat to ask also, or at least to tell us that you want to ask a question, and then maybe I'll call you. So let's go ahead. Please send your question. So everyone is unmuted. So any questions, please? Okay, I see right now no one asking questions. Let me ask one question then, first question to start. Luis, in the relations that you showed later towards the end, where you compared abundances versus solar system planets, especially the water was much less abundant. I wonder how far, yeah, especially this one, this graph, thanks. How far could very typically very different temperature regimes that the exoplanets have that we are able to observe nowadays, how far could that be responsible for this significant difference to the solar system planets?
Sorry, could you rephrase that? Do you mean?
Could I rephrase it? In this relation here, you compare to the solar system planets. But they are all cold planets, and the planets that we have transmission spectrum on are all rather hot ones, warm ones, hot ones. How far could that temperature difference affect this?
That is a very good point. The coolest planet that we have here has an equilibrium temperature of 290 Kelvin, right? Whereas that's roughly habitable, right? Whereas Jupiter is much cooler. So it is important to perhaps get measurements of the gas giants, which are significantly cooler, to know how important this difference is. Thankfully, and almost by coincidence, after we published this work, updated values from Juno came for Jupiter. So I am showing in this plot, this is different from what we published, but this purple dot, this purple arrow bar, is the current estimate of oxygen abundances in Jupiter. And here we see that it is consistent with the trend, but it also has a lower error bar that is consistent with stellar. So for a planet that is significantly cooler, we see a superstellar enrichment with current measurements, relative to the much hotter planets that show a substellar measurement. So I agree. It is important to look into this. Based on current observations, I wouldn't be able to say significantly that the temperature of the gas giant planets being so much colder is the reason for this.
Okay, thank you. Yeah. Good. Any further questions, please? Well, don't be shy.
I'm glad it was that clear.
Well, in lack of further questions, I guess we should all thank the speaker.
Thank you very much for having me.
Yeah, we should thank the speaker. Let's see. For this very nice talk. Many thanks. I look forward that you may be able to visit sometimes our institute.
I would love that.
Yeah, I'm aware that you have collaborated before with some people who are here in the audience, so maybe they will be interested in inviting you again.
Thank you.
And then thank you. And now I'm not aware of what is our seminar schedule, but please have a look at our website, and I guess we have a few more seminars before the summer break. So thank you to Luis, and good luck with your PhD thesis, and I guess we'll meet at some moment. Yeah, then thank you. Bye bye.
Bye now.